Okay, so I guess we are all set. Just going to quickly check the audio. Okay, so I guess we are all set. Welcome everyone to this week's PNS on processing memory. And today we are going to wrap up the semester, and we are going to discuss some of the adoption challenges that one needs to face when adopting processing memory systems to the current systems. And we are going to give a little bit of more focus on how you can ease the programmability of current real processing in memory architectures. There are several barriers that we need to address in order to enable processing memory architectures in current systems. Sorry. And those barriers exist because processing memory architecture fundamentally shifts the way that we look at computation, right? We saw during all of these weeks that we are moving from a vanilla paradigm, a processor-centric paradigm, to a memory-centric paradigm. And but at the same time, our current systems have been designed around the assumption that compute is compute and memory is memory. So for us to fully enable processing memory, we need to go through the computer architecture stack, starting from application software and understanding, for example, which applications would benefit from processing memory solutions, how we can interface with the hardware via compilers and hardware support, how we can enable, or what's the type of system integration that we need to port to the processing memory system, for example, what is the type of coherence and synchronization primitives that you need to enable so that you can enable tightly coupled processing memory architecture, how we can develop runtime and compilation support for scheduling computation across the many processing memory cores that you might need in your system, or how we can deal with data mapping and access control. And we need also to develop infrastructures that allow us to quickly test and check the feasibility of a given processing memory system for a given application. So all of this can be achieved if you change our mindsets. And if you look at the computer architecture step, as I mentioned, we need to go step by step across each level of the computer architecture step so that we can address the integration challenge the processing memory solutions might pose to current systems. So I'm going to highlight briefly several of our attempts in Safari to try to deal with these processing memory system integration problems. And like in the beginning of the semester, we discussed already PIM-enabled instructions, which starts very simplistic, just giving the main memory some really small computing power. So only a single instruction that operates over a cache line can be executed on the memory side at a time. And we saw that simplifies a lot the memory integration that particular processing memory system would require on current systems. Then I'm going to discuss a little bit more how we can enable programmability of real processing memory architectures by using some frameworks that abstract away the hardware organization of the processing memory systems. And I'm going to illustrate that in two works. The first one is what's called DaPPA, and the other one is called SimplePIM. So really briefly, we saw during the semester the real processing memory system, the PIM system, and not only the PIM system, but other architectures as well, as like the Samsung and the SK Hynix one, all follow a loosely coupled acceleration model. where the process memory system is viewed as a side accelerator for data-intensive applications. So usually, if you treat your process memory system like that, as a tightly coupled accelerator, loosely coupled accelerator versus a tightly coupled accelerator, that would require the system or the programming model to enable you to do several things. For example, if you have two memory address spaces, one for your host applications and the other one for your PIM-enabled applications, you might need to split the input data and the computation across the different memory spaces and across the different process memory chips. And you need to then transfer the input data from main memory to the process memory architecture. Then you need to manually handling caching. You may need to handle caching inside the process memory chip, in the particularly for the PIM architecture. You need which has some scratchpad memories inside the PIM cores. The user is responsible for moving the data from the DRAM banks in the PIM chip to the scratchpad memory prior to a computation. And finally, you might need to transfer the data back from the process memory chip to the main memory chip. So this model might be a little bit counterintuitive based on what we have been discussing during the semester, that you want to minimize data movement, and this is true. This model does not fully address process memory main benefits, does not leverage process memory main benefit, which is coupling computation together with the main memory of your memory chip so that you can minimize data movement. However, there are two assumptions here. First, if you loosely couple your PIM system as accelerator to your system integration becomes significantly easier because you don't need to handle things like coherence or address memory space, shared memory address space between the host application, which are quite challenging integration problems that we are going to discuss next. The second thing that this model enables is that the assumption here is that the amount of input data that you're going to operate or going to transfer from main memory to the PIM system, and the output data that is produced from the PIM system and eventually needs to be moved back to the main memory, that data movement is that the amount of data is going to be less than the intermediate data that is going to be produced during the computation. So hopefully the data movement, the total data movement you sum the input data, the output data, and the intermediate data produced is going to be less than doing the entire computation in the whole CPU core. So talk in particular about the PIM system, which has some SDK that enables programming the architecture using that execution model that I just mentioned. The programmer is responsible for several key tasks. Next, I'm going to show some code snippets of a vector addition implementation for the PIM programming model. So the programmer has several tasks that needs to be translated into code, including data alignment within the process memory chip, collecting input parameters, distributing input parameters across process memory cores, launching the PIM computation, collecting PIM results, manage the PIM scratchpad memory, and orchestrate data movement and compute across the different process memory cores. However, the programmer's main goal is to just perform a simple vector reduction operation which requires a few lines of code. So we conclude that programming the PIM system leads to non-trivial effort from the programmer, since it requires knowledge of the underlying hardware and manual data movement handling. So our goal in this follow-up work that I'm going to mention next is to ease the programmability of the real process memory chips, in particular the PIM chips, allowing the programmers to write PIM-friendly code efficiently. So now I'm going to introduce our first solution, which is called SimplePIM. So our software framework, SimplePIM, leverages the massive memory bandwidth and parallelism offered by PIM hardware to operate on arrays of arbitrary sizes and dimensions. SimplePIM offers three key interfaces to support PIM systems like UpMem. So first, the managed interface stores metadata for PIM resident arrays which can be accessed by the programmer and other parts of the SimplePIM as needed. Second, the communication interface provides abstraction for both host to PIM and PIM to PIM communication patterns. Those patterns are similar to communication patterns in other distributed frameworks, such as API, which makes it easier for SimplePIM to be adopted. Third, the processing interface leverages PIM high memory bandwidth and parallelism to execute map, reduce, and iterate PIM arrays. Programmers can combine these iterators to implement many widely used workloads, ranging from simple vector addition to complex machine learning models. So let's check each one of those interfaces next. So we start with the memory interface, the management interface. So the management interface provides two API, the array metadata to describe PIM resident arrays, and the simple PIM management for managed PIM resident array. And it supports two main operations. The first one is a lookup, which retrieves all relevant information from an array, register to register the metadata of an array. And then you can also, of course, free the metadata to free out the space of the PIM resident array. Then we have the communication interface. So the first communication interface allows for host to CPU a broadcast data movement, which basically takes an input array from the host main memory and broadcasts this input array across all of the DRAM banks of the PIM ports. The second interface for communication is for a scatter. So here we take an input array from the host CPU, and we scatter this input array across different DRAM banks across the different different PIM chips. Then we also have gather, which is the Caesar API from the scatter, which basically collects data from the different inputs from the different DRAM banks across the different PIM chips and combine them in the host main memory. Then we have PIM-to-PIM communication primitives. The first one is the all-reduced interface, which is commonly used for algorithms that require synchronization. And basically here, the programmer specifies an accumulation function, which is applied across the data that is moved from one PIM memory to another PIM memory. And this function is then operated over the input elements that are involved with the computation. Then we have always a gather operation, which basically combines arrays from different DRAM banks in the PIM chips and combine them and distribute them across all of the process memory ports. Then finally, we have the processing interface. So the first processing interface is a map operation. And this map operation applies a function across every element of input data, generating another output array of the same dimensions as the input array. Then we have a reduction operation, which applies a reduction function across the input element of the output arrays and accumulate the output values onto our output array. Finally, we have a zip operation, which takes two input arrays and combining them into elements of a third output array. So we also apply several code optimizations to SimplePIM backend so that we can accelerate the execution of the process memory cores. So these optimizations include strength reduction, loop unrolling, avoid boundary checks, function aligning, and adjustments of data transfer size. So we evaluate SimplePIM in a real PIM system with more than 2,000 process memory cores, and we evaluate that for 6 real-world applications from the PIM benchmark suite. So we compare the hand-optimized PIM implementation of those 6 workloads in terms of programming productivity and performance compared to SimplePIM. So here I just may briefly show a code for the histogram, a hand-optimized histogram implemented in the PIM benchmark. As you can see, you don't need to understand this code, but you can see this code has many lines of code. And by using SimplePIM and those 3 APIs that I described earlier, we can significantly reduce the number of lines of code required to implement the same histogram code. So here I just tabulate the lines of code reduction for those 6 real-world applications. And as we can see, SimplePIM reduces the number of lines of code significantly from almost 3 times to almost 6 times for those workloads. So hence improve program productivity. Then we conduct 2 studies, a weak scale analysis and a strong scale analysis for those 6 workloads, and we compare SimplePIM implementation with the hand-optimized implementations. So we first see that SimplePIM achieves comparable performance for 3 workloads, reduction, histogram, and linear reduction compared to the hand-optimized implementation, and outperform 3 other workloads, vector addition, logistic regression, and k-means by 10% to 37% for the 3 other workloads. And we see similar scaling when you do a strong scaling analysis. So SimplePIM scales better for 3 of the workloads compared to the hand-optimized implementations, and even outperforms 3 of those workloads, vector addition, logistic regressions, and k-means by 15% to 43%. So SimplePIM is available in your GitHub repository, and I invite you to check our paper if you want more information regarding SimplePIM. Then we move to DaPPA. So DaPPA is an improvement on top of SimplePIM, which uses the key idea of leveraging intuitive data parallel pattern-based programming interface for process memory. So DaPPA uses such an interface to automatically distribute and gather data across process memory chips, handle memory management, and to parallelize computation across cores. So the DaPPA is composed of 3 main components. First is a collection of data parallel pattern APIs, a data flow programming interface, and a dynamically template-based compilation model, which I'm going to illustrate next. So the data parallel pattern APIs are a collection of predefined functions that implement high-level data parallel pattern primitives. So DaPPA uses such APIs to implement a skeleton programming model, which is commonly as a common approach to abstract hardware components of parallel architectures, include multiprocessor systems, GPUs, and custom accelerators. DaPPA supports 5 primitives, including map, reduce, filter, window, and grouping. The user can also combine all 5 primitives for more complex patterns. So DaPPA exposes a data flow-based programming interface to the user. So the interface has 3 main components. First, a pipeline defines a collection of transformations of input data. Second, a stage defines a parallel pattern-based data transformation. And third, a stage communication happens sequentially with data following from one stage to another within the pipeline. So DaPPA uses a dynamic template-based compilation to generate PIM code in 2 main steps. First, DaPPA creates UpMem code using a template engine called Inja. Second, DaPPA applies a series of transformations to the codes to extract the information required to fit the UpMem code template from the pipeline model, calculates the memory offsets for automatically handling data movement, and divides the computation between CPU and process memory cores, even allowing for the collaborative execution between host cores and PIM cores. So during the dynamic template-based compilation, DaPPA compiles and executes each pipeline stage once per time, allowing for runtime optimizations based on the output data. So let's see how DaPPA can be used to implement a simple dot product operation in the UpMem system. So first, the programmer chooses suitable data parallel patterns to represent the computation. In this case here, we are going to use a map and a reduced parallel patterns. Second, the user creates 2 pipeline stages in C++ to implement the computation. Note that there is no hardware-specific code required over here. Finally, DaPPA takes the C++-based pipeline and dynamically compiles and executes each stage in the UpMem PIM system. So we evaluate DaPPA using a real UpMem system with more than 2,000 cores, and we use 6 workloads from the PIM benchmark suite in our analysis. So we compare DaPPA's performance in programming complexity against the hand-optimized PIM workloads. So in this plot here, we show DaPPA's performance normalized to the hand-to-PIM implementations. And we can observe a large performance improvement for some workloads due to DaPPA usage of parallel data transfer, the collaborative host, and PIM execution. So overall, DaPPA provides 2.1 times the performance of hand-tooled code. Next, we evaluate the programming complexity measured in lines of code. On average, DaPPA reduces the required lines of code by 94% compared to the PRIM implementations. So we briefly compare DaPPA to the SimplePIM. Compared to SimplePIM, DaPPA provides a high abstraction level where the user does not need to manually specify communication across PIM cores and host cores as well. 2 more data parallel patterns and further optimizations as collaborative PIM plus host execution. We conclude that DaPPA improves the state-of-the-art PIM programmability. So I invite you to check our DaPPA paper for more details on DaPPA. So now we address the PIM programmability issue, but there are many other system integration issues that needs to be addressed. For example, how can you maintain, if you don't follow a loosely coupled acceleration model, if you follow a tightly coupled accelerator model where the PIM memory shares the same memory as the host memory, we may face data coherence problems. So how we can enable coherence execution between PIM cores and host CPU cores. And we address this in this paper called Lazy PIM, which we show that by employing currently employ standardized coherence models, we significantly lose performance, but compared to no coherence. But by applying Lazy PIM, we can gain some of that performance back. We further improve Lazy PIM on this work called Conda, also for coherence, and we address other system integration problems as well. For example, how we can enable synchronization primitives to be implemented efficiently across memory cores in SIMDRAM, how we can enable virtual memory support for PIM cores in this paper called IMPICA, how we can perform code and data mapping between cores, PIM cores in transparent offloading and data mapping of paper. And we already discussed here in this semester how we can identify workloads that suffer from data movement bottlenecks and may suffer and may benefit from process memory offloading using the DAMOV methodology. So I briefly mentioned those works to just show that it's quite challenging to enable process memory in current systems, but we can address them one step at a time if you think differently. And by thinking different, we can fundamentally enable more energy efficient, high performance systems with minimal data movement overall. So just some concluding remarks. So this semester here, we saw that we need to start designing more balanced, high performance and energy efficient systems all the time. And this requires us to design more intelligent systems. And those intelligent systems are usually data-centric, data-driven, and data-aware. We need to enable computation capability inside or close to the memory if you want to have more balanced, energy efficient, and high performance systems. And this can lead to order of magnitude improvement in terms of both performance and energy, enable new applications and computing platforms, enable better understanding, which can enable us to have better understanding of the universe around us. So the future for truly memory-centric computing systems is quite bright. We're just starting. We just need to do more research and design better architectures across the computing stack, one step at a time. And this, again, would enable us to fundamentally design better data-centric, data-aware, and data-driven computer architectures, which revisits several assumptions on the way that we design systems today. So for all of this, we need to have good principles. We need to have more data-centric systems, more intelligent components, better cross-layer communication across interfaces, better than worst-case designs. We need to enable heterogeneity, flexibility, and systems that can adapt to different use cases. And all of this can be done if we keep our open mind on the way that we design computer architecture systems today. So this concludes the lecture for today. Hopefully this gave you some directions on what is next for process memory, or what is how we can enable process memory in current systems. I hope you enjoyed the lectures during this semester. Thanks so much for joining over YouTube, and I'll see you next time. Thank you very much.